Thank you very much for that introduction. Yeah, it's a pleasure to be here. It's probably the 7th or the 8th time at the GPD. I'm going to be talking about high-performance coated bent tempered glass today. And I would like to, take you onto a journey through the glass bending technology a bit in order to create the base foundation for what I would like to talk about in general, which is the thermally bent curved glass. So high performance coated bent tempered glass is one technology in our bending range of applications which we can apply to a glass panel. And what you see in this conference, today, where so many people are talking about curved glass, gives us that assurance that curved glass is actually becoming more and more popular in the architectural industry. We don't talk about straight edges anymore. We are curving edges in order to get them smoothly in line with the architectural lines of how those designs would like to go in line. So high performance tempered glass needs to be taken into account where we are thinking about what other technologies are in the market which are being applicable to a glass, get it into a certain shape. First things first, just getting you an overview about all the different topics I'm going through, which is more like an introduction, and that introduction is more related to other technologies in glass bending as well. We are going through, the whole mechanics of bending glass without a thermal impact. We are, going through different application methods as well as processing methods of how to bend a glass with other layers involved as well. Until we are finally coming to the heat bending of glass, which then evolves into the temper bending of glass. So you see, there are, many different kinds of technologies in how we can actually form a glass into a shape. We will talk about online bending glass, which is more or less the temper bending technology, looking at limitations as well as opportunities. And it's quite interesting that, the speaker before this presentation, Naomi from Eckersley of Callahan, has touched that kind of, a standardized method of how to measure distortions in temper bent glass, and was looking for the right solution of actually tracing those imperfections. And I guess we will see a possibility to actually trace these imperfections with a corresponding measurement method during this speech. I wasn't able to, look at her presentation before, but if I would have, I would probably have, put more slides into that, because that's a method which is practicable and can be implemented into the entire fabrication as well as inspection process. Furthermore, we are talking about some best practice cases as well as outlooks and new developments in temper bent glass. So let's start with a total different topic. When we are talking about high performance coatings, I'm always thinking about what is high performance, right? Are we actually, asking ourselves the question of what is high performance? What are we actually anticipating to how we identify that kind of claim, high performance? So high performance is in principle everything which is better, faster, more efficient than something which has been done present before. So it's like a high performance car or high performance running shoes, or it's a high performance coating on a glass, which has a specialty which makes this glass more efficient or more cost engineered. When we are talking about high performance glass, and it's quite interesting to actually pull this claim out. It's not only a coating, but it could also be a specialty glass, could also be a specialty shape, which makes that glass high performing, right? Structurally high performing. Of course, from a structural point of view, we could also use that glass in order to, eliminate any additional supporting elements like aluminum mullions or steel transoms in order to create a better shape to make it more stable. So bending of glass, you probably have seen all these different bending technologies what are out in the market. There are variation of different kinds of technologies of how to put a glass into a shape in order to resist in that shape rather than let it sprung back. There is a possibility of cold bending glass, which is more or less the most practical, less expensive, and mechanical part of how to put a glass into a shape. So what I'm doing is I'm just using a force to bend or warp a glass panel into a corresponding shape. So then we do have the warm bending process, and everybody has a different identification between those different kinds of technologies. So I call it warm bending. Warm bending is for me having a flat sheet of glass and putting that into a composite. Putting that into an oven or an autoclave, and at the end of this fabrication process, what I'm getting out is a curved glass which has a shape which is not naturally to that pre-introduced shape the glass had before. Hot bending is the very typical technology of how to put a glass into a shape. Hot bending is the typical slump bending process where I'm putting a glass into an oven for a longer time, reaching a high temperature where the glass actually transitions from a stable to a soft state, and let it get slumped from a gravity point of view into a shape. And then we do have the temper bending process, which is more or less a so-called online bending process where the glass is being put into a corresponding shape by force as well as through a tempering process. So starting with cold bending, as I said, I'm just carving out some advantages and disadvantages in order to get to a point where we can actually put all these different things in a clear comparison. So cold bending is in principle a flat piece of glass which I am glazing into a frame which is not flat. So that frame is either curved or that frame is warped. So one corner is out of plane. And I'm putting force onto that glass in order to get it pushed into that frame and restrain that mechanically. So, which means the glass is, still flat, but there's stress already involved. So the advantage is it's quite a economical glass fabrication because I don't have to have a bending process. So I'm actually putting everything into the post-fabrication process. The disadvantages are it's quite a difficult scheme in regards to warranties because all the glass is under stress, and if I do have an insulating glass, there is even more stress not only on the glass but also on the edge parameter sealant, which needs to stay over time. So it's not like it just needs to stay for a month or so. It needs to stay for 10 years. Because the warranty, which we always need to give, is for insulating glass 10 years or more. Even people would like to have 12 or maybe 14 years on insulating glass. So therefore, it always is a problem which needs to be coordinated between the glass fabricator as well as the installer. It's a complicated shop or field installation because, again, I need to bring pressure onto the glass with corresponding jacks or whatsoever, depending on how big the glass is and how thick the lights are. And there is a permanent stress which also needs to be pre-engineered into the glass, which probably makes the glass thicker than it was before. So then we do have this warm bending, which I call warm bending. Some people call it still cold bending. The warm bending of glass is in principle a lamination process. So I do have two sheets of glass, putting an interlayer in between and pressing this composite into a shape before it goes into the autoclave. Under heat, under pressure, the elements will attach and bond to each other, and once everything comes out, it has a corresponding shape. The problem with that shape is that the tolerances of those laminated bent panels are quite large, so there is kind of a spring back effect on edges, and again, same like with the cold bending, there is a possibility of actually delamination over time, where we still have the stresses involved into all the different glass layers. So the glass is in principle just trying to set itself apart. So there might be a durability issue later on. But again, the advantage is semi-economical glass fabrication. Then we have the hot bending. Simple process, put the glass into an oven and heat it up to a transition a temperature in order to get it slumped down onto a corresponding shape. And then we do have the temper bending. So the temper bending is following the same principle, however, tempers the glass at the same time. So what comes out is a tempered glass rather than an annealed glass, which has advantages in terms of having higher stresses or higher surface compression in the glass, which works more on the economical side of glass fabrication, because the process of temper bending is just a fraction, or uses just a fraction of the time of the conventional hot bending. And what I also can do is I can actually, put high performance low E coatings onto the glass and temper them correspondingly. Because high performance low E coatings are sensitive towards high temperatures under a corresponding longer time frame. So the shorter I'm actually restraining this time frame, the glass is being tempered or affected by high temperatures, the better the corresponding low E coating will stay and survive. Disadvantages, like every other tempered glass, are the distortions I'm putting onto the surface. So I do have distortions like roller waves, like strains, like all the other bows which are coming with tempered glass. And even if I'm tempering and bending that glass at the same time, these distortions are actually multiplying itself. Of course, we will see that there are other distortions which are being implemented onto the glass surface as well. The process is easy. We do have a machine which is using a corresponding tempering chamber where the glass is being put into under a high temperature of between 580, 620 degrees, depending on glass panel sizes as well as thicknesses, in order to uniformly heat the glass up before it goes into a cooling chamber, which calls quench. And this cooling chamber, compared to the flat tempering process, is kind of unique, because that cooling chamber is actually the area where the glass is being formed to a corresponding curve. So that cooling chamber is already preset in a certain radius, depending on how I would like to achieve that corresponding curve. It's in principle a higher sophistication of tempering glass, because this kind of cooling chamber also has a corresponding wave pattern or roller pattern, which also includes more more risk towards distortion in glass surfaces. Online bent tempered glass is, from a application point of view, usually being used in a one-directional bend application. Of course, it's difficult to, online bend temper the glass in two directions. So, because it's more like a run-through process. If I would, like to have a double curve in that glass, I would need to go to the conventional method of hot bending in order to actually get this to a corresponding shape. So therefore, it's more like related to a corresponding one-directional bend, which varies in radii depending on the glass thickness as well as the corresponding glass panel format. Bending of high-performance coatings, that's what we touched already. So there is a possibility to take low-E coatings, not the lower-performing low-E coatings like a single silver or a double silver coating, but also the triple silver coatings into consideration and apply those onto a glass before it's going to get through a temper bending furnace, because the beauty on that kind of process is that the period of time, the higher temperatures are having an impact onto the glass is fairly short. So therefore, there is a possibility of using those coatings in order to create a high-performance bent glass, which is then matching flat glasses in a corresponding glass facade, without any kind of, variation in colors. What we need to know is that usually what these low-E coatings they want to get under compression rather than under tension. So therefore, there's also a difference in whether I'm bending a low-E coating in a concave or convex shape. So 95% of all low-E coatings are actually nowadays are going to be bent into a concave shape, because the concave shape makes that kind of low-E coating, which is not facing the rollers, to a corresponding compressive state. So if I would like to have the low-E coating on the convex shape, then the low-E coating would be under tension, which those coatings typically don't like, because they are getting under stress. There is a possibility, of course, in different radii ranges where that is possible as well. General takes to consider are that the temper bending will likely be only process high-performance coatings rather than just using corresponding lower-performing coatings in terms of hot bend glass. The coating always needs to face the opposite surface of the rollers. So I never, put the coating onto a surface which touches the rollers of that machine because of potential scratches as well as damages. The minimum bending radii or radius shall be 800 millimeter, with keeping the coating under compression. And the feasibility of smaller radii could also be tested in a corresponding custom application. So what we do have in terms of limitation and opportunities, there are a whole lot of limitations out in the market, what we can do with temper bended glass. I don't go into the details over there. That would probably get us into a too long conversation about what we can do. Nowadays we can temper bend 18-meter long glass with a arc length of 3.60 m, 3.30 m if it needs to be low-E coated. In different radii, every furnace has a different kind of setup, which also determines the minimum radius in relation to a glass thickness. What we actually want to take from this is where are the limitations and opportunities. So what we have heard in other conversations today is how can we actually trace and track and measure those imperfections on the glass surface. So this picture shows you what we do have. We do have roller waves because it goes through a tempering furnace. But we do have actually not the typical, only the typical roller wave, which goes usually by parallel to the short edge of the glass. We, in temper bending, we do also have the roller waves which are going on and running by parallel to the long edge of the glass. Just because that kind of furnace is set up like the quench goes in that direction and creates corresponding waves onto a glass surface. So, and this is something what we need to deal with once we are getting into a kind of measurement process. How can we actually identify those imperfections, and how can we make sure that those imperfections are going to be controlled? So there's a possibility of actually doing this. So you all know probably the roller wave gauge, what you take and run over a glass surface in order to measure the corresponding roller waves. That's a bit difficult in curved glass because the surface is curved. So what is being possible is, and that's more like a practical way rather than a photogrammic or laser orientated way, is that you actually can use the same roller wave gauge in order to run it over the surface and measure the corresponding differences, deltas between surface imperfections, which gives you a good opportunity to actually get an understanding about how large that kind of imperfection in a certain area is, which creates a corresponding blurish in the glass. So usually you are starting with making a corresponding visual mock-up, and this visual mock-up is becoming the benchmark for your entire measurement. And then you're going and measuring over the surface at 3 points, at the bottom, center, and at the top, corresponding imperfections, which are in small increments next to each other. Creating this and putting that into a custom project individual standard based on that visual mock-up panel gives you a good alternate option of getting those corresponding roller waves under control. Again, we could, have talked about that a bit more in detail if there would be more time, but that's an interesting practicable way of actually doing this and solving the problem my speaker in before this corresponding presentation had. So best practice cases, just a quick run through what we are talking, buildings like that. So where we are, marrying flat glass with curved glass. And when we are talking about curved glass, not only curved glass in one direction, but also in two directions. That tower, for example, has flat glass on the large facade areas, goes around the corner with a corresponding convex-shaped glass and runs into that kind of setback with a concave-shaped glass. What we don't want, or maybe what the owner and the architects don't want, is they don't want to have a shift in color, right? So if I'm shifting color, that kind of, general picture will not look like that. That's a possibility what we can do in tempered bent glass. Of course, there is a way of actually putting the low E coating on the same surface, even though, it is concave or convex. It all depends on corresponding dimensional limitations. Large glass can be, applied with a corresponding low E coating. Very typical applications where a temper bent glass makes more sense because of that higher performance which is required. That's a project which is just laminated glass but bent, and that makes it not less higher performing. So of course what actually the owner wanted to have here in that project is he wanted to, nail down to a certain level of distortions, because that building is located in a prime location, and the glass which is being placed into that building is right in at the ground level. So he didn't want to get, distortions on the glass in order to, get, people, finding this more unattractive, like dealing with corresponding wavy structures. So what actually has been done there was that kind of measurement process where 100% of the glass is being checked, controlled, measured, and compared to a corresponding benchmark panel. Another unique way of using temper bent glass is again going into the tempering process and getting out a glass which has higher surface compression. Especially in that project, we do have a glass which has a big notch. So that notch is incorporating a door. So, and this could only be done with tempered glass. So if we would have used annealed glass, we would have to have, incorporated another joint, either horizontally or vertically. Another project where the curved glass has been correspondingly put into as making this whole facade more higher performing. Outlook and developments. What shall we do with double curvatures? There is a possibility which comes up probably during the next month or years where we can also double curve a glass within the temper bending process. It has been done, but it still, retains in a smaller limitation of dimensions. So the only problem is that I really need to run this through the corresponding, online process, which makes the arc height, small in comparison to larger spherical curves, which are coming up with, arch heights of a meter or even more. Another possibility or opportunity is a corresponding smaller radius, which was not, possible before. Nowadays, there is also a possibility to temper bend a small tight radius of about 170 millimeter and get this kind of, shape married into the application of temper bending, and probably over the time also find coating which can be applied into that tight radius. So many tests have been done in regards to that in order to verify the corresponding tempering. Seeing an annealed glass which breaks based on that ball drop test. Having the same glass in a tempered version is creating a much safer application in glass and glazing. So, and what I wanted to talk about as well is more like a summary. This is more like a glass bending design toolkit, not for you because you may know all these differences already, because you are dealing with glass and glazing every day. It's more like it would like to push this out into the architectural industry, because usually what we are dealing with as contractors is we are finding people who don't know. You start designing something which comes out in a process of design engineering, and getting turned around into a complete, total different product or total different application later on, because they haven't had that kind of knowledge before. And this is just something which should be given into a guideline where there are several things included of maximum, minimum dimensions, as well as the corresponding comparison between warranties, behavior, coatability, as well as cost. Because everybody is concerned about cost, right, at the end of the day. So the owner needs to, or the architect needs to have a clear understanding about cost in comparison, between the different technologies and what a corresponding technology gives to the project, which one cannot. Unfortunately, we were out of time, but I would like to thank you for your attention.
So many thanks, Dirk.
Hi there. Did you like what you just saw? If you did, why not like the video drop us a comment below, as well as share the video with others, since GPD is all about sharing. And to receive more videos in future, subscribe and don't forget to click the bell icon for notifications. Ciao!